Okay, good morning. And yes, the work that I present today, of course, is the result of a collaboration with quite a number of my colleagues at TU Delft and also beyond TU Delft. So I'll speak about measurements, and I will try to give you an impression of what can be done, where have we moved from the community of experimental fluid mechanics, in particular flow diagnostics. I'll put some focus on 4D and vortices. But given the scope of this symposium, I would like also to spend some time on the specific topic of vortices, definition of a vortices, and to contribute to the discussion about vortices. After that, I will speak about visualization, but mostly measurements, and then we enter PIV. I will show a number of applications, and when can we meet spatially resolved 3D conditions, and in some cases, if we have a proper equipment, temporarily resolved. And in water, it's easy, in air, it's less easy because the speeds are higher. I will give you a glance of some recent developments of large-scale PIV, and then conclude. So these are vortices, and I wanted to do a kind of a voting session, but let me not spend the time on it. I think we have very little doubt that Kelvin-Helmholtz vortices are vortices. They should be considered vortices with an uppercase V. This might sound trivial to you, but I will move to other examples and manifestations that we might doubt whether they are vortices or not. So these are clouds, Kelvin-Helmholtz, a beautiful visualization, the cat eyes here. Also the tornadoes in their scary layout. I think many of us would consider them vortices. And this also the beautiful edge effects of wings or rotors producing these trailing vortices. These are streamwise vortices, whereas these are mostly, they are born span-wise. So these are all vortices. These ones, I think we might also not debate that much. The Carmen Street, it's maybe the iconic picture of a vortex. If you give an impulse, a pulse jet, like even the dolphins can do, and then you generate a vortex in water, and cavitation will help you visualizing it, so it's called a bubble ring vortex. In some condition, if there is enough moisture in the air, the tip vortex of these propellers would cause such a low pressure and temperature, especially the temperature, that then you get a condensation. And condensation will then make the vortex region visible, like here. And here, instead, this is artificially made visible. This is an experiment in water at Onera. It's an old experiment, and then they were very carefully injecting ink of different colors, yellow and blue and green. Often in France, they use the 3 colors of their flag, and to visualize the delta wing vortices. So far, so good. I think we should not debate that much. Okay, the problem comes here, at least for me. Now, if you take an object and you look at the wake of this object, and instead of looking at the beautiful time-resolved evolution of it, you time average the flow, as we do in many engineering applications. I see I hear echo. Do you hear the same echo? Does it disturb? No? Okay. If you are comfortable, I go on. Away. Yeah. Maybe here. Yeah. Okay, so let's look at this wake. Now, the wake, at the end, if you integrate, if you accumulate the events hundreds of times or thousands of times, the flow will converge to this shape or to this shape. Now, what do we see? We have a focus. We have a point or an axis around what you have some streamlines. Of course, these are the time average streamlines they evolve. And so the question, is this a vortex or not? My personal take on this problem, I think it was presented by others, is that I would not include this in the family of vortices, and I will explain why. Because if, after we have accepted all this family of vortices, and then we focus ourselves on vortex detectors with specific local conditions, maybe the local condition of this type of vortices is quite different from the Kelvin-Helmholtz and the Kalman vortices, then we risk making our problem on vortex detection and definition even more complicated. So, let me see here. Yeah. So, but this is just words. A way for me, I was thinking a little bit over the past days that have been very instructive to follow all this presentation. I see the difference of these vortices, even the lead-driven cavity. There is one difference with respect to the other type of vortices, is that if you move from the center radially out, in all these cases, what happens is that you move along the radius, and the maximum tangential velocity actually is reached outside of the region of closed streamlines. I would say just let's think about that. It's a different topological condition compared to the Kalman or to this type of vortices, where you get the closed streamlines within the maximum tangential velocity. So, let me continue. If we want to go even to the full paradox, we go in the textbooks of aerodynamics, and then we have the airfoil and the thin airfoil theory, which models the circulation around an airfoil with a multitude, actually with an infinity of very tiny infinitesimal vortices. And Professor Liu might not agree at all that these are vortices, because there is no swirling motion there, but still in the textbook this is what you would read. And it says that there is a vortex distribution that gives you the vorticity sheet and that produces the circulation around the airfoil. Now, if I ask myself the question, is this a vortex? Should I have a vortex detection method have a positive outcome when I say this is the flow around an airfoil, even an inviscid flow around an airfoil? So this is food for thought. Okay, let's move to visualization. Visualization, we have seen a number of visualizations yesterday, but I will move on to quantitative. The beauty of visualization is that at a glance, it gives you the full pattern of the flow. This can be done with the smoke lines, with the timelines, with the hydrogen bubbles. If you are an artist in the field, you can play with spatial intermittency and temporal intermittency and produce very nice patterns. All goes well until turbulence kicks in. And because, as you can see here, for a turbulent flow, the contrast of the picture becomes increasingly degrades because the scalar diffuses. I think we saw in a previous presentation. So when the scalar diffuses, then we cannot understand the pattern anymore. So this is the limit of flow visualization in turbulent flows. How to solve that limit? We need a tool that does not diffuse in time. And then we have to go from a continuous release of a scalar to sparse emitters that do not change their property in time. So we need particles. And that's where PIV comes into the picture. Yeah, this is, I think many of you must have been familiar at least with the concept. You put these sparse particles in the flow. They should be small enough that they follow the flow with fidelity. Then you illuminate them in a confined region of space over a sheet in the previous setups. And then you have a camera following these particles in time, and later on with some algorithms you follow them, you track them, or you make a cross correlation. So the dream is to have the velocity vector in x, y, z, and t, such that you can even make derivatives, and then we can apply our nice methods based on the gradient analysis. Yes, this is, some of you with the good eyes will see when I toggle between the two images, so the particle moving, then this motion is revealed by vectors and contour plots for velocity or contour plots for vorticity. Here we can see the vorticity sheet then wrapping up into the Kelvin-Helmholtz, the section of Kelvin-Helmholtz vortices. Okay, let me start with now a first example of an application that was very relevant for vortex wake research, aircraft wake turbulence. So we all know about the formation of these vortices, and there was a presentation yesterday speaking about how critical it is for the aircraft separation length at the airports when they take off, so you should not really, the problem of vortex wake encounter. You can have a loss of altitude, you can have a roll, or even damage of some of the structural components of the aircraft. And the larger is the aircraft, and the longer this wake is supposed to persist until some vortex instabilities kick in, like the Crow instability, and then destroy the coherence of this vortex pair. And we have also seen yesterday the split and reconnect mechanism of these vortices. How to study that? This is the largest, one of the largest wind tunnels in Europe. It has a very large test section of about 9 by 9 square meters. And you put an aircraft, yet even in this tunnel you can study up to 6 wingspans in the back, which is completely irrelevant for this type of problem, because you need to know it at hundreds of wingspans, which is the position where the next aircraft will cross the wake. And yet we don't have a wind tunnel that continues until the center of Arlington. And so the strategy for this type of analysis then is to change a little bit the system of reference. Instead of moving the air, actually you go back to the original problem with the aircraft moving and in quiescent fluid, as it is in reality. But in this case, we did it in a towing tank in water, just because it turned out to be simpler to have the control of the aircraft. So this is a towing tank, a small one in Delft, but then the experiments were repeated in another larger towing tank in Rome with a half a kilometer length. And this was a pilot experiment. Also, our other colleagues tried with the catapult system. So the aircraft was actually thrown in the air and crossing a region with PID particles and with lasers. But I will only report about this. So this is the approach. There is a laser sent down into water. And then when the time passes, you can transfer time into space. Of course, x is t times v in this case, and the camera is placed at some angle in order not to hit the aircraft. So there is a little correction to be done for this angle. This was my first work when I was employed at TU Delft more than 20 years ago. And these are some of the results. So the full aircraft in the fully at scale is traversed across this light sheet, and we can see the vortex being formed in the early stages. This vortex is more complex. Let me repeat it for a moment. In the early stages is more complex because it emanates from several discontinuity on the wing, but little by little it wraps into a single vortical structure with on this side of the aircraft. Of course, you have to imagine the opposite on the other side. And if you increase the angle of attack, of course, you will find a more intense circulation and vorticity. And we concluded that even this towing tank was not enough, because after around 140 wingspans, the vortex motion is influenced by the presence of the walls. So the vortex starts producing its mirror image. Yeah, this is a synthesis of the evolution of these vortices, and the path of the vortex, and the overall circulation shows that we are quite far from the condition of a vortex being self-destroyed by the instabilities or being dissipated, because circulation is still constant after 140 wingspans. Yet, in those years, it was very fashionable. The industry was thinking of having actuators on the wingtips and try to stimulate, accelerate the formation of these crown instabilities, and these are from some proposal from Boeing, but we have not seen it on real aircraft, so something clearly didn't go as expected. The second part is, again, related to aviation, is the use of PIV to study the complex fluid dynamic situation in swirled combustors. And of course, in this case, one cannot simulate the entire physics, including the combustion, but in a water facility with a swirler with vanes, one could capture, I will explain, this is done with time-resolved tomographic PIV. This is the Vortex skeleton. In gray, it is the jet, this swirled jet, and then these colored isosurfaces are isosurfaces of Q criterion and colored by the axial velocity. So we can see quite a beautiful arrangement pattern of Kelvin-Helmholtz instabilities on this highly distorted flow. And again, another challenge comes from the jet noise. One of the subsequent innovation, the problem is that the regulation are more stringent about noise around the airports, and to lead to some designs. And this was another experiment done, again, with a tomographic PIV. In this case, it was with a high-speed tomographic PIV, a simple jet, a horizontal circular jet. And here, again, we can see the Kelvin-Helmholtz vortices. Some of them are disappearing, and maybe it would be nice to look with the vortex detection system that they don't really disappear, but in fact, they decrease their intensity because they are trapped into the leading vortex. And you can see that right after this leapfrogging, it's called leapfrogging mechanism, and after leapfrogging, then the azimuthal instabilities explode, leading to more and more isotropic type of fluctuations. Let me see this. This is an experiment done with the large wind tunnels in the Netherlands, which is a consortium of German and Dutch wind tunnels. Here we have used the PIV implemented onto a robotic arm to produce a three-dimensional analysis of an aircraft in full propulsive mode. The aircraft is put upside down. That's the way how they test it, because the balance comes from the top. And then these are the seeds that I will talk about, the helium fields or bubbles, and then the robot will scan, by combs, will scan the aircraft and produce a picture. Let me try to accelerate it, if I can.
4 or 5 minutes.
Oh, 5 minutes. Wow, time is really flying. Okay. Then I will move on to, yes, okay, let me put to this. Okay, yes, it all looks nice. I hope you can see the hole here, the black hole. And this is a PIV picture, and we were discussing now on the bus. One of the problems of these particles is that they are centrifuged from the central vortices. So PIV looks nice because you can study vortices, but what's the point if they are centrifuged from the core of vortices? So no method can be applied just because we have a void of information. And why? Because the particles are heavier than air. Actually, heavily heavier than air, 1,000 times more. And this is a scheme that shows you the trajectory of a particle heavier than air, HTA, and a particle that is instead lighter than air. So is it possible to engineer tracers that are lighter than air such that we will have back some particles in the core? And this is what can be done with helium fields or bubbles. These are engineered type of tracers, a bit larger, of course, 0.5 millimeter or 300 micron. And they are filled in with helium, and they have a very region of soap. such that the buoyancy parameter is close to zero. And if the buoyancy parameter is close to zero, this means that they will act neutrally with respect to the streamlines. Yeah, these are experiments, these are the droplets, and these are the helium fields, so bubbles. If you make them slightly heavier than air, you still have the hole. If you make them slightly lighter than air, actually you have an overpopulation in the vortex core. That's very good. It's good news for PIV. And by this, for the first time, one could obtain data that in the vortex core, this is tangential velocity, this is the axial velocity. Often you have a PIV data at high speed that is interrupted in the middle, and so you do not know if it is, for instance, a jet type of axis or a wake type axis, but then using this type of bubbles, one could solve this problem. And I think I will jump over the techniques to make tomographic PIV. But to say that the state of the art at the moment is even beyond tomographic PIV, but the state of the art gives you this three-dimensional picture of particles. So from the images, you go to the three-dimensional position of the particles through triangulation algorithms, and then you can either cross-correlate or you can even track the individual particles. And as a result, you can now, I think I should put a stamp. This is not a simulation. So these are experiments. This is data coming from a laboratory in the back of a real cylinder in this case, at low Reynolds number, because this was a camera with a low frame rate in water, and it is a slightly larger Reynolds number. This is a vorticity magnitude maps to show the genesis of these vortices from the shear layer separating from the cylinder. But I would be really thrilled to see how the Vortex operator would give us a sharper picture of these vortices. The same can be done, as I did here in water with high-speed cameras. In this case, the temporal resolution is much higher. And then as you move in air, the things get much more complicated because the speed is higher and the particles are tinier. So the region that you can measure becomes immediately much, much smaller because of the laser budget. And this was an experiment with Sinagami, and we needed to multiply the laser light by using mirrors to bounce back and forth to have more light. This is something is explained in this Measurement Science and Technology article, this light amplifier, which would be used to study the boundary layer at the trailing edge of a NACA airfoil. And this is an example of the result. You see much less impressive in air because a little light and a smaller region, still one could see the organization in the high and low speed streaks and the vertical structures being horse riding the low speed streaks. I can move now to, yes, we did, following the inspiration of Fazl Hussain and workers, we tried some coherent structure induction and defining a first prototype for these hairpin vortices, and we found there were also counter hairpin vortices in the wake, and count how many of these vortices would be present in the population, similar to what we have seen yesterday with this vortex labeling, but quite a handmade and laborious process. So let me see, I have now just a minute. Now, how do we move to large-scale experiment, and why do we need to move to large-scale experiments? In some cases, the scaling imposes the scale of the experiment, or the complexity. You cannot miniaturize things that are complex, like a helicopter. You want to act on real system, and when the human body is to play a role, you cannot miniaturize the human body. Only in fiction movies you can do that. And in order to obtain this large scale, we need to scale up the seeding, and helium filled soap bubbles has been the solution we have mostly engineered. But some people have done it even in the open field with snowflakes, but snowflakes have an important bias in terms of slit velocity. So I go back to this, so the beauty of this type of technology is that they scatter 100,000 times more light than an individual droplet. So if you get so much more light, you can relax your parameters in terms of field of view, in terms of widening the laser or the LED, and even the mechanism how you produce them, you can make them neutrally buoyant from very small scale. Actually, we found them down to 100 micron, up to a few millimeters. So it's a scalable now, a scalable tracer that could fit size from a liter to a few cubic meters. And to produce them is quite complicated. To make droplets is just vaporize some solution, and then they form droplets. But to produce instead of the bubbles, it's like making tortellini one by one by hand compared to the crazy chef here. This means that you have to engineer this system with a multitude, with hundreds or even thousands of generators. So it's quite an expensive exercise. So it's still not much practiced, but I hope to see it more in the field. And then the result is that you can study systems of the order of several meters, which this is a video taken with an iPhone. So you can see how much more contrast you get in these pictures. Given that the time is up, I will conclude with this result. The most recent result is from our colleagues of DLR. They have flown a drone in a room, and they could measure the entire multitude of particles that track the complex vortical structure from the helical vortices down to the dissipated turbulent wake of this aircraft. Thank you for the attention.
Yeah, thanks for the very interesting talk. I mean,